Hey guys, Alex here from the University of Wollongong. In this video, we'll dive into the idea of capacitance and the effect of capacitance in a DC circuit. Before we start, it's important to note that you should always be precautious when working with any electrical components. This includes capacitors. If you touch the terminals of a capacitor, these can result in an electric shock. So, without further ado, let's dive into it and begin with a refresh on direct current. Direct current, or DC, is the unidirectional flow of electric charge, generally in the form of electrons with one or more voltage sources. In most cases, this voltage source is a battery. This means that current flows in one direction in either a series or parallel circuit. From high to low potential, that is described by the voltage of the power source. So, in direct current, we can only have one direction, whether it be high to low or conventional, low to high. Capacitor, on the other hand, is much like a battery. It's a device that is used to store electric charge. It consists of two electrical conductors, known as electrodes. They are separated by an insulator, known as a dielectric. So capacitors are often measured in farads, which describes coulombs produced per volt from a capacitor, though we often deal with capacitors with microfarads. Paired with capacitance of a capacitor is the voltage in which it can retain. Unlike a battery, a capacitor stores far less energy, though it can charge and discharge much quicker. We'll get into why this is useful a bit later. This is just an example of a capacitor, which will always consist of the capacitance in farads, in this case, 4,700 microfarads, and the voltage in which it can retain, which is 35 volts. So, what's another thing to acknowledge is it's important that whenever dealing with capacitors, you never have the voltage source exceed the voltage on the capacitor, as this could result in overloading the capacitor and cause it to explode. So why do we use them? When a capacitor is charged, it stores equivalent voltage to that source, as we just mentioned, that charged it. When the source is cut off and current stops flowing, the capacitor will discharge and keep current flowing. So if this is a 12-volt battery and we have current flowing, it'll continue to flow until this capacitor is full, for which case it'll act like an open circuit. No more energy can go through this capacitor. It's like if you were pouring water into a sponge and the sponge filled up, no more water can pass through that sponge. But in the same instance, if you turned off that tap and were to squeeze the sponge, you could produce an equivalent to the water that was being stored in that sponge. This is the exact same situation with the capacitor. If you were to open this switch, stop this voltage source from producing any flow, the capacitor would discharge and produce this 12 volts and complete the current until it completely dissipated. So an example of one of the main uses for capacitors is to keep a current steady when a power supply is swapped out. As the energy stored of the capacitor is being dispersed, the current will continue, allowing for the correction with the power supply. The more capacitors, the more the time is multiplied. This is also the case if you were to have a larger capacitor in equivalent to a larger voltage source. So if you were to take a battery and it was supplying power to this circuit, and then you remove the battery out of the equation, all these capacitors would have been charged to 12 volts, and they would keep the circuit going, allowing for time for this battery to be swapped back in, and preventing any flux in the circuit and preventing any stoppage of flow. So it's important to understand how we calculate capacitance. The main formula that you'll need to know is charge multiplied by the voltage across the capacitor multiplied by the capacitance in farads. It's also important to acknowledge how we add capacitance to get total capacitance in a circuit. It's very similar to resistors in the sense, but it's also not very similar because it's inverse. So if you were to take capacitors in series, you would take the inverse of each capacitance and take the sum of those, and that would give you your total capacitance, whilst in parallel, you would just take the sum of all the capacitors. Very counterintuitive, but becomes easy to remember once you practice. There's also a formula for charge/discharge, where we take the time constant tau, and we also take the time in seconds it takes to charge/discharge the capacitor. Thank you.